Oh, yeah, sure. Sorry. We're already running over.
Yeah, when it's okay from the...
Oh, you need the signal from those guys? Okay. And can I test this? Is this on?
All right, welcome back everyone. My name is Ralph Dolmans. I'm a member of the OARC PC. In this session we will have 3 DNSSEC related talks, with the first one being from Shumon, Huque and Jan Fialak, and they are going to talk about multi-signer DNSSEC models.
Okay, thank you, Ralph. So I'm Shumon. This is my partner in crime, Jan, over there, and we're going to talk about multi-signer DNSSEC models and why. So let's skip over the abstract. I'll start with a little bit of background. At OARC 28, so that was March of last year, I introduced this topic very briefly towards the end of a talk that I did on DNSSEC for large enterprises. After that, we kind of fleshed out these models in a protocol specification document that we presented at IETF a few weeks later, and subsequently there's been more work. So it's been adopted by the IETF working group. We've done some work on prototypes and early implementations. We've talked to a number of commercial managed DNS providers who have expressed interest in implementing these models. So in order to understand the rationale for these models, it's best to start by describing what the traditional multi-provider model is today. And that is one in which the zone owner runs a master server that maintains the authoritative zone data. It signs that zone data, and then it pushes out the signed zone to multiple providers via standard DNS zone transfer mechanisms. So this is a very well understood model. It's been deployed successfully in the field many times by many folks. But it has one notable limitation, namely that it doesn't work with a certain class of non-standardized DNS features, often dynamic features, but still that are quite widely used in the DNS industry today. So what are these non-standard mechanisms? Well, they have many names, but they're commonly referred to under a term traffic management, so that's the word I'm going to use. And they include things like GSLB, Global Server Load Balancing, probing and failover, record pools, even custom scripted responses. These are often querier specific or at least dependent on examining some sort of dynamic state in the network. So necessarily, the answer and signature has to be determined at the authoritative server that is answering the query from the client at the time of the query or both. Now, let's see, I'm going to embarrass Paul by mentioning him again. You may be aware that Paul famously critiqued these features in an article that is almost a decade old now. And he had a cute name for these features, which I'm not going to repeat. But he had several cogent arguments. So he says that these features arguably increase the complexity of the DNS. They make it harder to debug and troubleshoot. They're a layering violation. And they represent also a form of cost shifting from a set of application providers to DNS infrastructure operators. So all of those arguments you may agree with, and yet we can't really deny the reality of how pervasively these mechanisms are already deployed in the industry today. So this is a long-standing tussle. We think these features are here to stay, and DNSSEC is just going to have to grapple with the reality of them and accommodate them, right? So one more point I'll make on this topic. If you may recall, if you attended the ICANN DNS symposium, not the one that just ended, but the one last year, Paul Mockapetris, the inventor of the DNS, made a remark in his keynote that perhaps the DNS will evolve to start storing not only data, but programs as well. And in a sense, that's kind of what's happening with these features. So you might argue that we're already heading in that direction. or at least in a sense, right? So there's a link to the presentation there. So let's talk about the multi-signer models. So these are models in which multiple providers cooperatively serve the same zone data, but they do it in a way that each provider independently signs the zone data. Now, these models are able to support even these non-standardized DNS features if the providers in question are capable of signing the response data generated by these features. And I should mention that this is not universally the case, so some providers can, some providers can't. The ones that can, the common strategies that are in use are online signing or on-the-fly signing. That's probably the simplest way, but it's not the only way. So if it's possible to enumerate all the answer RR sets in advance, which is often the case, you could pre-compute the responses and their signatures and then determine algorithmically at query time which response set and associated signature to return. So all those things work. So the main additional requirement we have here is we need to carefully manage the contents of the DNS key and DSRR sets in such a way that validation is always possible no matter which provider's authoritative servers you query and get the response from. And the strategy that we suggest in our protocol document is that each provider has to import the zone signing public keys of every other provider into their DNS key RR set. So this seemed like a very straightforward solution to us, but when we initially presented this work at the IETF, we got a lot of scratching heads, and people weren't able to grasp exactly why this requirement was being imposed and how it solved the problem. So I thought I'd walk you through that problem in a little bit more detail. So the easiest way to understand this is to consider the behavior of a validating resolver in the presence of a zone that is independently signed by multiple providers. So let's take an example zone, let's say example.com, and the case of two providers A and B. Just for simplicity, our model is generalizable to any number of providers. So the first thing that has to happen is that we get a referral, a secure delegation from the parent zone, from the COM servers to example.com. And this contains signed DS records probably pointing to both providers' key signing keys. The next step is that the resolver has to go and fetch the DNS key RR set for the zone. Let's say it chooses to talk to provider A. It gets the response, which includes A's KSK and ZSK, and we cache that after matching it to the DS record hashes, right? At some later point in time, the resolver queries another record in that zone, let's say www.example.com, but this time it talks to one of provider B's name servers. It gets the response, but now we have a problem. That response is signed by B's ZSK, which is not present in the cached DNS key response that we obtained earlier from provider A. So if you just stare at this slide for a few seconds, the solution will be obvious, and that is provider A's DNS key response needs to include the ZSK for provider B and vice versa. And just to generalize, every provider has to import the zone signing public keys of every other provider. So I should mention that even if you were not to do this key sharing thing, things could in some situations kind of work or mostly work, and that's because resolvers tend to be very, very aggressive. So if you get a bogus response from one server, they discard it, they keep trying until they get a validatable response, and then they move on. But this is kind of a very precarious situation to be in, because you don't know when some resolver is going to give up after a certain number of failed attempts, or worse, downstream clients of the resolver may have timed out and moved on. So really you want to avoid this situation. And I'm going to now turn it over to my colleague.
Thank you, Shumon. Shumon said the answer is obvious. So we have to somehow keep the DNS key record set in sync for each provider, and then it will work. So in the draft, we actually describe two models how this can be configured. The models differ in how we essentially deal with the key signing key, but we always use a dedicated zone signing key with each provider. It's relatively, in short, summarized on this slide, but I would much rather demonstrate this on this diagram. So we have this sample zone, example.com, that is delegated from the parent. So the delegation contains the NS record, and the NS record will point to both of the providers. That's the beginning. And now we have to enable DNSSEC. So for this purpose, each of the providers, the provider A on the left, has their own set of zone signing key, and the other provider on the right has a different set of zone signing key. The zone owner, who in this model is actually responsible of building this DNS key record set, holds the key signing key. So this is not, this key signing key is never shared with these providers. And the zone owner collects the public keys and builds the DNS key set, signs it, and pushes this signed DNS key record set to both of the providers. And it also has to include the public key signing key in the DS record in the parent zone. So in this diagram, you can see that the DNS key record set is always served with the same signature, because that's the signature is generated offline by the zone owner. But any other content in the zone, for instance, the www example.com quad A record, is signed by different keys in the end, by the different providers. So this model uses 3 keys, but there is still some responsibility on the zone owner, and we want this model to also work where the zone owner says, I trust these DNS providers and I want them to handle DNSSEC completely. I don't want to keep key signing key in my data center and perform some manual operations. So from this reason, we also describe a second model, which we call model 2. And this model adds an extra key signing key. So now the key signing, now we have a dedicated pair of key signing key at each provider. So we have 4 keys in total. And the principle is the same. We always have to keep the DNS key record in sync. We can just sign it with different keys. So in this model, you can see that each set of records, even DNS keys and even DNS key records, are signed by different keys. And to make this work, we also have to include the other KSK in the parent zone, and it will work. It's described in the document. This is just the link if you want to read it. Comments are welcome. And there are a few more things that should be considered. For instance, the signing algorithms. So we have realized that it's important for the providers to use the same signing algorithm. It's not always necessary, but it's better. One aspect is more practical. If you have 2 different signing algorithms, they have different security properties, and the security of the whole system will be defined by the weakest algorithm. So that's one reason to have the same signing algorithm. But there are also validators in the wild that are too strict and require signature being made by each algorithm at the same time. This has been a problem with some older version of Unbound. It's probably not true at the moment because there's evidence that some TLDs were able to roll to a different signing algorithm without actually double signing the zone. So it's just a should, it's not a must. And of course, if there's a validator that has only partial algorithm support and supports signatures made by only one DNSSEC provider, it means that it will accept only responses from this provider and not from the other. So that's also interesting to consider. And NSEC, that's a kind of special case. The NSEC or denying responses in DNS are always self-contained. They will contain all the NSEC records or all the information and signatures that are needed to validate whether the answer is authentic. So we think we don't necessarily have to use the same NSEC mechanism like NSEC and NSEC 3, for instance. But it's probably better because, again, some validators employ aggressive NSEC caching, and this might negatively impact this mechanism if 2 different providers serve different NSEC at the same time. I will quickly mention key rollovers. This multi-signer model doesn't bring any complication to this model. It's still pretty straightforward. There's one section that in the draft. We promised to talk about some implementation. So after the last ITF in Montreal in July, we actually tried to validate these models. We set up some DNS servers, made sure it works. And just after that, we started thinking about if the providers were to implement this, we have to have some common interface that the providers need to agree on. So I work for NS1. We are really interested in implementing this. We talked to different providers. Cloudflare, for instance, expressed interest in implementing this as well. So we talked to them and we settled on, we came with the basic requirements, like how an abstract API should look like to support this model. And it appears that it's not that complicated, and it's actually very close to the interface that most of the providers already have. So one operation that is definitely required is that we need to be able to collect these public keys from the providers. So there needs to be some operation to retrieve the public keys that are intended to be used to sign that zone. And then there needs to be a second mechanism to push the DNS key record set and optionally signatures for the DNS key record set back to the provider, so the provider can serve it without doing the usual like signing stuff. Again, I have some diagram that describes this, these steps. So again, we have two providers. They have some abstract API. The API could be anything. It could be DNS dynamic update. It could be REST API. There are of course, some other option. And then the zone owner, or what we like to call key manager, just goes to the providers and retrieves the keys. It adds, in the model 1, it adds the public key for the KSK and builds DNS key record set, CDNS key record set, CDS, whatever is needed. It issues signatures for each of these record types and pushes it back to the providers so the providers can serve it. So we have actually already implemented this. It works in our testing environment, but of course we are looking for integration with anyone else. So if you are interested in this, definitely talk to me. And the model 2, it's very similar. There's just the missing middle step where the zone owner or key manager need to sign the records. But otherwise, there's nothing special on it. And with that, I would hand it over back to Shumon because he did some testing with open source servers.
Yeah. Okay. All right, so I'll talk a little. We've also experimented with open source implementations to find out how easy it is or isn't to support some of these models. And our quick initial assessment is if you're doing offline signing, that means your signing is happening outside of the running name server and then you load the sign zone. It should be possible to make these models work without any problem because you can stitch together any configuration of DNS key, importing, exporting foreign keys, whatever you need, and that should just all work. The slightly trickier configuration is one in which the name server itself, the running name server process is signing and maintaining the zone continuously. So there you do need some explicit support in the name server code, but it turns out some of these implementations already have some of that support. So Bind actually has a tool. This is not widely used because not many people have figured out much of a use for it, but it's called DNSSEC-import key that allows the running name server to import a foreign ZSK without any accompanying private key, dynamically update the zone, and it does all the right things, including respecting all the key timing metadata, et cetera, et cetera. So with that mechanism, Model 2 just works out of the box. Model 1 is a little bit trickier. I don't really have time to talk about it, but if you're interested, I can elaborate later. And we're looking at other implementations. I'll just mention one other one. So there is actually a talk later this afternoon from CZ.NIC about a feature that they have called the offline KSK and not. So I'm not going to mention anything else about it other than to mention that it turns out that's exactly the mechanism you need to implement Model 1. All right, so let's switch gears a little bit and talk about another topic, inter-provider handoff of sign zones. And what I mean by that is how to cleanly migrate a sign zone from one provider non-disruptively to another provider. And by non-disruptively, I mean that you cannot break DNSSEC validation at any point during this process. So this has actually been a source of occasional frustration in segments of the DNS industry because there appears to be no standardized scheme to do it. So we think the multi-signer models could address this problem, at least in theory, assuming cooperating parties are involved. So the multi-signer model assumes a steady state configuration in which you have multiple providers signing the same zone continuously. However, that configuration doesn't appear out of magic, right? So you have to probably sequentially onboard one signed provider at a time, and then you may decide at one point you don't like provider B, I'm going to toss it out and bring in provider C, so you need an offboarding process too. All of these mechanisms are part of the multi-signer model. And if you think about it, that includes all the stuff that you need to hand off a zone to another provider. So this problem is essentially just a transitional state of the more permanent multi-signer model. And standardizing a scheme will probably help. We have people from the ICANN community who have expressed interest in working with us to see if we can provide them with a kind of a sanctioned solution to this problem. Of course, that involves, the technical piece is probably the easier part of that discussion. There's a lot of policy stuff involved. So if anyone knows anything about the situation in ICANN or wants to help us out with some of those discussions, feel free to get in touch with us and we'd be happy to chat in more detail. Okay, a few other issues that have been brought up in the course of developing this draft. One is compatibility of the traffic management features. Remember, a lot of these things are proprietary features of a particular DNS vendor. And the question is, can you really compatibly deploy these features across multiple providers? And the answer is it depends. There's usually a baseline of features and functions that almost all of them support, like GSLB, getting you the response with the closest servers, failover pools, et cetera. Those kind of things just seem to work. More or less. Load balancing, very accurate load balancing is a little bit of a trickier problem. So in some cases, you may need to augment the authoritative DNS systems to talk to external systems. But it turns out that some providers, I think Jan's company is one of them, already have hooks to talk to a variety of external systems, extract information from those systems, and use that in the decision to select a response. One more item that occasionally we're asked about, why don't you just standardize these non-standardized features, right? And then, so that seems, it's easier said than done. It's probably, number one, it's probably a fairly daunting task if you consider the range of possible features that these vendors implement, number one. And number two, we've actually had some discussions about this with managed DNS providers, and almost uniformly we've gotten resistance because they consider these non-standard features their secret sauce and their competitive advantage, right? So they're really not motivated to standardize any of this stuff, so I think that's a losing game. And the last item that I'll mention is several people have brought up the fact that maybe we're causing problems. We might be introducing problems by bloating the size of DNS responses. So the quick answer to that is in these models, the size of normal responses are unchanged. It's only the size of the DNS key response that is bigger. So the question is it big enough to cause any problems? The answer to that probably depends on a number of factors. Your choice of algorithm, for algorithms that support varying key size, the choice of key size, the number of providers involved. So if you're using 2048-bit RSAs, ESKs, and KSKs, and you're using 3 or 4 providers, I admit you might run into some problems. If you're using ECDSA, which is what we've almost uniformly tested with, there doesn't seem to be any problem at all. So I'm just gonna leave you with one more slide of a test that we did just to produce some numbers. And sort of the base response with 2 providers, ECDSA P256, some average length second level domain, and minimal responses. So we're not stuffing anything any extraneous information in the authority and additional sections that are not needed. The normal response is only 471 bytes. If we consider an active KSK rolling process, it increases to 580. And kind of the worst case scenario with two providers where we have one KSK roll and both the providers are rolling their ZSKs, you get to 740 bytes. So that is nowhere near the common internet MTU. So we just don't think it's going to be a practical problem. And so in closing, just to summarize the key points in this talk, many organizations employ multiple providers. Many of them use these non-standardized features, and we need to make DNSSEC work successfully in such environments. So the models we presented here are one way of accomplishing those. They can tackle other problems as well, like the inter-provider handoff case that I mentioned. We are actively talking to a number of commercial managed DNS providers. Some of them are implementing these schemes, some of them are interested in them. More widespread adoption would be good, so we'd be happy to talk to any interested parties about that. And lastly, we think open source implementations should provide the mechanisms to allow these models to work. And I see a queue at the mic, so I guess we will take questions. All right, come on up, Jan. We can't hear you, George.
That's all right, I'll shout. Hi, George from APNIC. Look, I've got kind of 3 small points, all right? And they're off to one side. Can you roll back to 20? While you're doing it, I'll do one of the points. You use the word provider in a couple of different ways. You use the word when you're talking about an active port 53 responding machine and the behavior it has in system. Mm-hmm. And you use it when you mean a commercial entity offering service to someone like GLSB. It's confusing. You've got to find ways to separate out your concepts about things in DNS from companies providing things in DNS.
Fair enough. Yeah, that's a good point. So, I mean, at one point I was thinking of using the term DNS operator. Maybe that would be more accurate.
But it's not a big deal. So, This slide, you've got a black key there called private for NSA. Yeah? See that? Black private key. Up on the top box, you've got a black key for COM.
Yeah, sorry for that.
You really did want to use a different color for that key, didn't you?
Yeah, I rotated the key because I ran out of colors.
So 23. So move forward to 23. This is the only real part of the question. If you roll forward to slide 23. Yay. I think that's too much of a story to put in a footnote. Seriously. You are saying that there is a requirement relating to algorithm use under differential behavior of different algorithms, and you're saying nobody does that.
Yeah, well, I mean...
That's a big story.
Yeah, okay, fair enough. So we put it in the footnote. It could have been a larger bullet item. So
I mean, if it's not a real requirement, can we maybe make it not be a requirement?
Yeah, so the reality is in the original DNS specification, there was a specific requirement, and that requirement was imposed on authoritative DNS server signing the zone, that they must be able to produce signatures of every algorithm in the DNS key R set. It is not actually a requirement that is imposed on DNS resolver operators. You could argue that it should be because it presents certain classes of downgrade attacks. But in reality, if you look at modern resolvers today, none of them enforce this requirement. And that's why TLDs like .br and .se were able to roll their algorithms without double signing anything. Okay.
Hello, Matthijs, Mekking, ISC. First, a small comment on the key sizes, which are on the DNS key sizes. One thing that you didn't mention, which might be consideration as well, is to use a combined signing key, a single key that has the role of signing the DNS key set and also the other R sets. So KSK and ZSK being a role applied on one key. The other thing I was going to mention is about, you mentioned this can solve the rollover between different operators. Mm-hmm. I think that has already been solved, unless you're talking about operators that are not cooperating. But that wouldn't be the case in this scenario, right? If you have multiple providers, they're likely going to operate with each other. And that rollover is being described in DNSSEC operational practices, RFC. That sort of works. If you're talking about non-cooperating, then that is the real issue, because we have not found yet a way to do a rollover of operator without going insecure.
Right. Okay, so just to make sure I understand you, Matthijs, you're saying that the inter-provider handoff is already a solved problem unless we have uncooperating parties?
Correct.
Okay. Yeah, so if we have uncooperating parties, I don't think our model actually helps solve that problem either. So the thing is, we keep hearing from people from the ICANN community and other communities that you need to come in and help us solve this problem. So I don't know where their frustration or where their reasoning comes from, but I think it's worth investigating. If a solution already exists, why doesn't it work for them?
Yeah, definitely. With the solution already existing, I mean, it's written down in RFC, but indeed, if it in practice means that there are some cases that are causing frustration, then that needs to be figured out.
Okay, yeah. So on your combined signing key questions, so I haven't really thought about it too much, but I think our models will work with combining signing keys too, right?
Yeah, I really don't see that much difference. Because the validators don't differentiate between key signing key and zone signing keys. It just needs to be, the signature just needs to exist. So I think it would work even with combined key signing key.
Yeah, I think it will work as well, but I didn't see it in the slides, that's why I brought it up.
Yeah, fair enough. So to be complete, we should probably address that case in the document so that people who want to use CSKs can follow a document and follow a recipe.
And the third thing is that the NSEC3 parameters being the same, I doubt that, but let's take that offline, please.
Yeah, they don't have to, because as I said, the answer is self-contained, so everything should be there. You could use NSEC and NSEC3 at the same time, but the resolvers that employ aggressive NSEC caching somehow need to deal with that situation, and they often can, for instance, keep only a single algorithm in the cache. So if you present them with NSEC and NSEC3 or NSEC3 with different salt, they might, for instance, flush the NSEC cache because they think NSEC rollover happened. And like I have to start building the NSEC cache from scratch.
I have to close the mic line and want to ask you to keep the question short because we're running out of time.
Hi guys, this is Anand from RIPE-NCC. Just a short comment. Last year, RIPE-NCC switched signers, DNSSEC signers, and this is essentially what we did. We used Model 1 with a ZSK cross-import, and then uploaded the DS records from both signers into the parents and executed a successful switch from our old signers to the new signers. So, this works.
Sure. Yeah, thanks. That's a very good, useful tidbit of information. On Model 1, another thing I just forgot is an observation was made to me that I hadn't realized a while back from David Blacka, who's one of the co-authors on our draft, that Model 1 is essentially the way the root zone is managed today. It's just the degenerate case of one provider, George, one operator and one key manager, right? Okay, carry on.
Petr Špaček, CZNIC. Will be brief. Thank you for your work. I like it. I like the analysis, and I agree with the proposal for the NSEC recommendation, because with my resolver implementer hat on, that's absolutely correct recommendation.
Thanks.
Hi, Mark Groeneweg, SIDN.nl. Thank you for a great presentation. I must mention that SIDN has now 4 students working on the inter-provider handoff to look in the timing aspects of the caches, and also on the fact that we hopefully make some policy developments for .nl as laat as het DNSSEC signed zone. So please get in contact after this meeting. Right?
Okay, will do. Thank you.
Eddie Winstead, ISC. I'm not sure that the cooperating operator thing has been solved. So thank you for this work. So I hear about this a lot and hear about people that deal with this sort of thing. So however we can help in getting the open source stuff where you want it, because I know a lot of this focus was on the commercial side, but please do let us know.
Okay. Thank you, Eddie.
Brian Dixon, GoDaddy. Great. One question, it's probably like a corner case, I'm not sure if you've thought about it, is where potentially you incorporate zones that are being served through a GSLB with a lot of different potential answers that would each be signed. I don't know whether that works on the associated with the NSEC, NSEC3 stuff, but has that something been tested or looked at?
So I think it does work, right? I mean, you guys support that, right? Yeah.
Yeah, like NS1 provides or performs online signing, so that's how we do that. But as Shumon mentioned in the beginning of the talk, there are different ways how to do that. You can pre-sign all the other options in advance.
Yeah.
So.
Okay, cool. Thanks.
Thank you, guys.
Okay, thank you.
Thank you.
Up next, we'll have Matthijs Mekking, who will tell us a story about unsupported DNSSEC algorithms.
Yes, a short, simple story on unsupported algorithms. So I started half a year ago at ISC, and I joined a team who is working on a name server, who's making the name server a modern name server to nowadays standards. And this comes with big refactorizations, but also with some smaller efforts, and this is a story about a smaller effort. That smaller effort is unsupported algorithms. We removed support for those algorithms that are basically outdated. We removed RSA MD5, DSA, GHOST. Nobody uses them anymore. I looked at Victor's measurements for TLDs. There's zero use of these. That becomes because there's better alternatives, or there are known weaknesses with these algorithms. So yeah, let's remove them. So is this effort as simple as just removing all the references from the code? Basically it is. But at that point we realized we actually don't have tests for how the name server reacts on when you encounter such an algorithm that you don't support anymore. So what do? We write the tests. This is actually not a new problem, but because RSA MD5 should have been removed like years ago, according to the RFC. And basically nobody understands algorithm 255, well, maybe in private networks, but you should have dealt with that. So you have to have code that checks whether you support the algorithm. So yeah, writing tests. Let's see. Also, as mentioned in a previous presentation, there may be validators out there actually that support one set of algorithms and the other supports another set. So in theory, it could be a real world issue, but there's, I think, a small chance that it will actually occur. Nevertheless, there's quite some places that interact with DNSSEC algorithms, and we were thinking, okay, how should it behave? We have a vague idea on how it should behave, and there's actually also RFCs that have some words on it. Mostly the RFCs has to say about this is that you will treat this as insecure, but it's harder to find what to do in some corner cases, which we'll see in a minute. So I wrote a test for that, and let's see, I figured out these are the common cases where you interact with a DNSSEC algorithm. Obviously, key creation, when you're going to sign the zone, you can still publish a DNS key record with an algorithm that you don't know about. And then there's the validation part. Trust anchors, DLV, I included that as well, and 5011. And especially 5011 is when you have in your resolver automated updates of trust anchors, but we'll focus here on when you do an algorithm rollover. And while I was looking at the bind name server, I thought, well, let's include all the other open source name servers. So these are the products I tested. Some relate on signing, some relate on validation, some both. You might see one obvious piece of software missing here, which is NSD, and that's because they don't do signing, they don't do validation, they just load the zone. Okay, for those who are not keen on looking at the details later on, these are the sort of the main observations. The good thing is most things just work, actually. I saw some quirky things which I will go into, and the ugly, I found some crashes. So let's look at the signers first. Tools, we are looking, some tools are creating keys and signing the zone. So I looked at the DNSSEC utilities and their relatives. And then there's software that has automated DNSSEC. So they don't rely on the tools to create the keys and do the signing, but you just provide them with a policy and it will just work. And third, for signing perspective, I looked at whether they allow a published DNS key with an unsupported algorithm. So key creation, if you provide it with a unsupported algorithm, should fail, right? Because you don't know the algorithm. This is sort of like the output I got from the name servers I tested. And yeah, they basically all work. So all good here. Well, okay, I want to highlight one thing here. OpenDNSSEC says key generation failed. Key generation failed. Doesn't say me why. So I think this can be improved. Yeah, I reported this issue, but it's a minor thing. The other thing is maybe interesting to see here is how PowerDNS handles it. It looks like they handle this on the parser arguments level. So they just allow a couple of strings as an algorithm, and if you provide something else, it just fails. Signing, second case, it should fail too, because if you want to sign a zone with an algorithm you don't know about, you don't know the crypto stuff, so blah. This is also a pretty good case for looking at DNSSEC sign zone in the first, on the top here. Basically what I've done here is create a key with algorithm RC MD5. And then put it in the key directory, set auto DNSSEC to maintain, and then fire up bind, and it will say, okay, I can't do this because the algorithm is not supported. It will go in the log file. PowerDNS the same, also gives a good message here so that you know what's going on. And then the next slide shows Knot and OpenDNSSEC. Knot also gives a good message, and OpenDNSSEC is basically the same. It says key generation failed, and yeah, that could be better. Third case, allow publication. We don't need to go into deep details here. Everyone allows a key there and just signs it with an algorithm that they do support. So signing is actually fine, not that exciting. Let's look at the validator case. Validator case basically have 4 tests that I looked into. The simple one is doing a basic query. Then I looked at trust anchors, whether they are ignored. The algorithm rollover and when they are dealing with 5011, and the DLV case. So this is a setup for the basic query. I'm doing a dig to one of the name servers. I've set up 2 zones. A zone example, which is like the parent zone with a DS record with algorithm 1, and on the child zone, which is signed with algorithm 1. I can do this, by the way, because LDNS sign zone still supports RSA MD5, so thanks for that. The results here, I'm going a little bit faster on the boring results because time is running out. all fine here. So let's look at the trust anchors. Are they ignored? So the setup describes is a little bit different here, but not too much. The only thing that changes is that we specifically add a trust anchor for the zone that is signed with an unsupported algorithm. Okay, some red here, so that means it has something to talk about. Good results for bind 9 and unbound. Interesting case for not resolver. Basically, it detects the problem here. It knows what's going on. It's like it says invalid key algorithm, but it panics in this case. So knowing about the problem, about panicking, I found it interesting. Power DNS has a different thing. It behaves different than the others one. The others ignore the trust anchor, but Power DNS says this is fine. I'm going to add this trust anchor, but only to figure out later that it can't use this trust anchor for validation. It will try, but it won't validate. The not issue has been fixed in the latest version in not resolver, and I've talked to Peter van Dijk on the latter issue, and he said in future versions they will add a warning message that this is not a good trust anchor. Let's look at algorithm rollover. The setup is different because we're starting out with a valid case, supported algorithm, starting up the resolver, and then doing an algorithm rollover on the authoritative side. And we expect that once the key is rolled to the unsupported algorithm, the resolver will catch that, will revoke the trust point at the point that the algorithm 13 in this case is revoked, and then the trust point will be deleted, and future queries should go validation status insecure. Okay, there's an image here, something to talk about. Unbound does what I expect to do. The others is the crashes I detected. So one is in bind. What happens here? So let's look at a piece of code. It actually it got the key set and then sees the unsupported. It sees the DNS key, but then it wants to try to compute the key tag. So it calls the function that does that, but it will return actually bad results because it couldn't complete that task. But there's a runtime check that says this should work, otherwise we can't continue. So that runtime check failed and has been fixed in 9.13.6 and later versions. But yeah, it resulted in a crash. Not resolver actually crashed in the same way when the key with the unsupported algorithm was added in the DNS key set, was fetched by the 5011 mechanism in the resolver. It got this panic, and this looks like the same panic as we had when we were trying to add the trust anchor. Again, I should have mentioned that both are fixed. Also, I would like to point out these are crashes that you could potentially happen on the internet, but they're very, very hard to exploit because it means that the adversary has to have control of the trust anchor that the resolver has configured. Last cases is DLV. There's two name servers actually only that support the DLV is unbound and bind. Basically, if you have an unsupported unsupported algorithm in the DLV, everything is fine. But also, I looked on the case where you have a DLV that actually has an unsupported algorithm there. And that is interesting, but it's because that show different behavior. So bind will actually say, okay, you have a trust point, and there is a key with an unsupported algorithm. I'm going to ignore that, so it's an empty trust point. So there's a broken trust chain, so I'm going to do bogus. And unbound says this is a trust anchor, not a trust point. So I don't know this algorithm. I'm going to ignore it, and then acts as if it doesn't exist, just like a normal trust anchor actually. And so the answers will come back insecure. So I actually don't know what the right behavior is. I couldn't find that in the RFCs. I think for both behaviors, something to say. It's just a matter of how you interpret this thing. What to me is interesting is that you have an object, a DLV object, which in different implementations have different properties. So in this case, it doesn't really matter because DLV is going to be decommissioned and this code should go anyway. But it shows that we have different views on objects, and so specification is not always clear. An overview of all the tests in the name servers. I listed here where the bugs that I found are fixed, or whether they're not fixed but the issue is reported. And to me this is a good picture because most of the things are green. So why tell this story actually? This started out to improve our Bind 9 test suite, and that should really lead to improved code. And also, when we did this exercise, was let's really look at where we can find the interactions with the algorithms, and we get to learn about the weird cases. So it's an educational purpose as well. So something I want to share with you as well. Also, I want to show you these boring results, like the tests mostly pass, and which to me shows that the DNSSEC implementations are quite good. So yeah, it's a positive message. But I only tested the open source vendors because it's easy to get a code, and I know there's many more DNSSEC implementers here, and that may benefit from this story. So they can learn about the clarifications as well, and maybe in your environment you can fix the unknown unknowns. Also, we're having this implementation guideline, and this is from the latest draft, and you can see which one are supported and which are not. And so, as mentioned in the previous presentation, yeah, you can have a transition period where one name server supports an algorithm and the other cannot, and you should be able to deal with that period. So, recap is overall good, bit of quirkiness. The crashes that I did find very hard to exploit. All fixed, very quick uptake from the DNS vendors to fix this. Well, one of us was IC itself, so hey. Implementation guidelines, bye-bye old weak protocols, and thank you for your attention. I am currently working and looking into how make DNSSEC easy, so in Bind. So if you have ideas about that, some frustrations, come talk to me because I'd love to help you out. And thank you for your attention.
Thank you, Matthijs. Are any questions for Matthijs?
Petr Špaček, CZNIC, thank you for reporting bugs, and I hope that the cooperation will go the same way, and we will report more bugs to you as well.
Jaromír, CZNIC, I was just checking to CZNode. I still see some of them unsupported algorithms there, so I wonder how they are signed, but they still exist, surprisingly. So it reminds me the question whether maybe one thing you could think about is also verifying the technical checks or delegation tools, for example, like ZoneMaster, because I don't think they behave the same. They support the level, if they find unsupported algorithm, that they should put an error message or something like that. That would be worth to also expand this to the delegation tools checking as well.
Yeah, that's a good addition. And also, I didn't look into the DS hash algorithms, and that could be checked as well. Maybe we'll do that in the future. Delegation things, probably something out of our area. Maybe somebody else can pick that up. And how they are assigning with an unsupported algorithm or an old algorithm. I mentioned LDNS sign zone, for example, still allows RZ MD5, so that's may explain how they are still signing those zones. Thanks.
Up next is Jaromír Talíř, who will talk about offline case in Knot DNS.
Thank Ralph, and thanks Shumon for a nice teaser in their presentation. So I'm actually going to tell you something about how the CZ zone is doing the DNSSEC signing, and I will tell you that we don't like it. It's and the way how we think that we can improve what we are doing. But the ultimate goal of my presentation is maybe to see if there is any other TLD or DNS operator generally who is doing something similar, to find out if maybe we can synchronize our effort and to build our tools based on not just our expectations but the general expectation. So after my talk, that I would like to hear from you. If there is such case also. So a little bit of history. The CZ domain was signed in 2006, so 13 years ago. At the beginning, we did some tests with some HSMs. There was that Sun card, but before we managed to operate it, I think that the Sun stopped supported that. So at the end, we decided that it's better to go operational with DNSSEC rather than to test more and more HSM. So we didn't start with HSM, and the responsibility for all the keys was fully in hands of our sysadmins, which we thought that definitely it's not a good idea. So we did a major redesign in 2013. When we decided to split the role of the ZSK and KSK into two teams. ZSK operations still remain in the hands of sysadmins, but we moved the responsibility for KSK operations to our CCERT people. We have a group of people responsible for CCERT, and they're skilled enough to manage the KSK operations. And the goal was to put the KSK offline into the safe, so that it's taken out only during the KSK ceremony. Definitely, this is something inspired by the root zone operation, so I don't say that something that we have invented, but we used a similar approach. So how our ZSK operations look like. We roll the ZSK every second month, and we decided to have the ceremony twice a year, KSK ceremony twice a year. So we pre-generate every half a year. We pre-generate 3 new keys, and we create a key signing request. And in this key signing request, there are all combinations of ZSKs that will appear in the zone file for the next 6 months. Then this package is signed by BGP of ZSK team just to give it some sort of authorization and sent to the KSK team. So how actually our key signing requests look like? It's a tarball with a bunch of files. Each file is for one include of DNS key records. You can see that there is a timestamp or time of validity of these records from 2, And then there are a key tag of ZSK that's included in this file. So this is actually the snippet of the zone containing only DNS key records. And you can see that, here. And you can see how the ZSK rollover during this period is going. And the KSK operations are based on the environment where we have the specific dedicated laptop with our Wi-Fi. It's not as official as for the ICANN, but a little bit. There is a fixed bootable image that we will boot in the laptop, and we have a private part of KSK in the safe that we take off and use for our ceremony. There are some multiple witnesses, signed report, a little bit officiality. And the output of the ceremony is a signed key response that is again signed and sent back to ZSK team. How this signed key response is generated, we take the public part of KSK that they are using and append it to each of those files. Then we must transform this file into the formal zone file. That means that we will add some template that we fill, like with the header of the zone file, and it's normally signed with this KSK. After that, the DNS key and RSIC are again extracted from the zone file, and the output is our signed key response. So this is again how this signed key response looks like. You can see here that in the name of the file, so we added also the key tag of the key signing key, and you can see that the validity of signatures is actually based on the dates that is expected them to be introduced in the zone file. So then the third part of this whole procedure is zone signing. That means that our registry system generates clear zone file every 30 minutes. We put some checks on this zone file, like we count the number of differences from the previous zone file. We verify with different existing tools. And then the appropriate signed key response file is selected based on the timestamp and included into the zone file. We also, to speed up a little bit, we take the signatures from previous signing and then the whole zone is signed with the ZSK based on the tag that is on the name of the file. So actually we have three set of shell script that we are using to manage all these operations. One for generating the key signing request, one for generating the signed key response, and one of the signing the zone. Those are shell scripts written on top of the famous tools from Bind and LDNS, like DNSSEC and SignZone, various checking tools, and yeah, it's interesting, I would say. So what are the challenges of this approach? Definitely, last year I had a presentation about how we did algorithm rollover to ECDSA. We had to modify those scripts a little bit to provide the proper way of algorithm rollover. But it turned out that it was better to write some small but little easier script from scratch and then throw it out than to modify those scripts, because looks like that less and less people understand what these scripts are doing, because the stuff is changing and the scripts are quite old. They were written by people, they not anymore work for us. And we had a big discussion between the two teams that we have, the DNS operations and the registry development, whose responsibility those scripts should be, because the DNS people said, well, it could be part of the registry, so we just want the zone file, and the people in the registry development, they said, we don't want to care about DNSSEC, that's scary, so keep that in your hands. So we had to definitely decide what to do next. And the ultimate question that we always need to answer is, why the hell CZNIC is using bind for signing and not DNS? So we were before in front of the question, can we also switch to automated signing? That would be really saves us all of this shell script hell. However, the way how we are doing that is not actually supported by any DNSSEC signer implementation. I saw that the offline KSK feature is on the to-do list of bind and OpenDNSSEC for second time, but nobody has actually, as far as I know, tried to implement it. So we actually managed to put the sysadmins together and Knot DNS developer together to work on collecting all the requirements, and the result was that the offline KSK support was implemented is the one of the latest version of Knot DNS that was released a few months ago. Just a small recap. I don't know if it's necessary to introduce Knot DNS, but still it's a DNSSEC, it's an authoritative DNS server with automated DNSSEC signing feature. The goal was to make it as simple that's just easy to turn it on and forget about DNSSEC. So it has many features like support for HSMs, CDS, CDNS key, and others. It can work in the way that it can accept the zone file via transfer, so it can be like bump in the wire signer. And we are glad to hear that last half a year ago that RAPE NCC decided to use Knot DNS as a DNS signer of their choice. They were using that for 116 zones, mainly the reverse zones, but a few of internal zones like RAPENet. And I've heard that Anand will have an update about their story in the next RAPE meeting. And I know also that the DNSSEC signer performance of all tools will be presented via Niels Harbo from DKOS Master at the Center Technical Working Group. So this is a small introduction that if you have not enough meeting after this one, just when you go back and get recovered from the jet lag, you can go again to the conference, to the RAPE, and to the center in Reykjavik in Amsterdam. So this is how the configuration of Knot DNS looks like. To enable automated signing, you can just put the DNSSEC signing on. Of course, you have to fill all these parameters for the algorithms. And how it changes if you want to enable offline KSK. So there's new feature, offline KSK on, and you must turn also the feature manual on. So this is probably the only change that you need to do on the automated signer. And there are a few modification of there is a tool, existing tool, Key Manager, that is used to manage all the keys in the Knot DNSSEC signer. And so there are new commands to this tool that actually should immediately they work in the way that I exactly described in the previous scenarios. So there is one command that pre-generates new ZS keys in the key database for next 6 months. Then there is a command to generate key signing request for this period, and Knot DNS people, they decided to slightly change the format, so the key signing request is now one single file where there are individual snippets of these that previously we had in individual files, and but otherwise the information is roughly the same. And then on the side of the KSK team, it's quite similar. On the first usage, if they just want to import or generate the new key, they have to call this generate. However, it's expected that they already have the keys in their database. So the only thing they just need to do is to take these key signing requests and transform it into the signed response. And this is again how the signed response looks like. The example. Don't be confused with algorithm 14. We are using algorithm 13, so this is just test. And then the output of the KSK team is again imported to the via key manager on the ZSK team side. And there is one last thing that they have to do is to signal the Knot daemon to refresh the state and load it from the database. Just one slide that the last Knot DNS 2.8 has more features regarding DNSSEC, more improvements. Mainly that there is a new multi-threaded DNSSEC signing, so it dramatically speed up the signing. And many other more. So what is the future? Definitely testing. That we have some maybe expected resistance of our sysadmin team to accept immediately new features. So they are now testing that, and hopefully we will migrate to this new scenario at the end of this year. Yeah, that's all from my presentation. I would really like to hear if there is anybody else who works this similar way and would like to maybe to give us some feedback if we can modify our tool to suit their needs as well. So thank you for listening. And I will answer a question.
Christian Petras, DNIC. You want to hear if somebody do the same way. We do this way at our legacy platform. We use the LDNS library and has written a script framework around this, generates snippets with a Python script, and this snippets is the same DNS key records, pre-compiled and pre-signed DNS key records, as you said. And then we transfer it with a USB stick to Subversion and check it in and rebuild our signing environment. But I have to say that we want to get rid of this really complicated key ceremony, but it's not just a problem of not or bind or whatever. It's mostly the problem of the role concept of the HSMs. And we are thinking about using soft HSM or something to get rid of this. And maybe an option could be that your key manager stores the keys if you have no HSM in CASPDB. If you have this encrypted, the key material encrypted, and in non-pageable memory, it's nearly the same soft HSM too. This could be maybe an improvement for the community as well.
Okay, thanks for suggestion.
Thank you. Really good work.
Thank you, Jaromír.
So, no other DNS operators having offline KSK? Okay. Thank you.
Before we start the coffee break, I have a couple of announcements. Jerry will be handing out tickets for the boat for tonight's social event. So if you registered for that, please go pick them up at the registration desk. To speed up the process, it would be good if everybody can have their Eventbrite QR code ready. Second, we are still looking for submissions for lightning talks, so if you have any interesting idea, please send your submission to submissions@dns-OARC.net. And lastly, please don't forget to rate the presentations by filling out the survey, of which the link should become available on the slides during the break. So we will be back again here at 4. Thank you.